idea behind the chain rule? Why not just go take the derivative right now? What do you mean it's nasty? What's nasty about it? If you did not have the chain rule, you would have to raise x cubed minus 17 to the 5th power. Which, do we have a way of doing that without literally multiplying or foiling x cubed minus 17 5 times? Or 4 times? Yes. How would we do it if we did have to expand it? Just really. Ah, Pascal's triangle. How does that one look?
Wait a minute, no. Oh, no.
Which level is it? The 6th?
The nice thing is, 1, 5.
10.
Does that work? How many terms are there? Why does it make sense that a 5th degree would have 6 terms? A squared has 3 terms, right? A trinomial. A 3rd power has 4 terms, 5 terms. Because it'd be a 5th degree, 4th degree, 3rd degree, 2nd degree, 1st degree, and then constant. True? Now, you might not have had that memorized. You might have had to build up. But if those are the coefficients, wait, how could we actually do that? How would we apply it to x cubed minus 17? I'm just reviewing the binomial theorem. What would your first term be? 1 x to the x cubed to the 5th power, because that would be your a. That's being raised to the 5th power. So yeah, that'd be x to the 15th. That's fun. And then we have plus minus 5 times. Oh, yeah, we have the 5 times the 17. Then we have the x cubed to the 4th power, which would be x to the 12th, right? Then what would be your next term? I know, most of you taking the SAT, ACT, and this isn't like a huge topic, but I'm just making sure you know the binomial here. That'd be x to the 12th. And then we would have plus 10 times. Do you see why it's a plus? Because a negative 17 squared is going to be a positive. And then x to the x cubed to the 3rd power. 3 times 3 is 9. Binomial theorem. This guy gets raised to the 5th. So cubed to the 5th is 15. Then to the 4th, 3 to the 4th power is 12. Then to the 3rd, 3 to the 3rd power is 9. As this guy starts at 0 power and then 1 power, 2 power, 3 power. One counts down as the other one counts up, right? Now what's the dilemma with this? I wouldn't have to go that much farther. I have 1, 2, 3. 3 more terms to go. So I'd have minus 10 and I have 17 cubed x to the 6th. Some of you see the pattern now. Now I have 5, 17 to the 4th, x to the 3rd. And then I have minus 17 to the 5th. But what would be the dilemma, even with Pascal's triangle? I still couldn't take the derivative until I did what? I'd have to multiply the little binomial by the, right? I have to do 1 by everybody and then 2x. So what's much more useful? Looking at f of x and seeing him to be what? Is that pretty much what you guys would have to do? Right? I have to look at f as being a g, a separate function, times an h. G times h is kind of like a product rule. But the h has a j inside. So from what you guys know about the chain rule, not even being specific, but being general, what would the derivative of f be? Oh, sorry, I meant just general.
So h of j of x times g prime x plus g of x times h prime of j of x times g prime of x.
You guys agree with Kevin? Now what John was starting to do was actually solving, because he was saying -2. He had done g prime. I'm guessing that you would have multiplied by that x cubed minus 17 to the 5th power. Plus, and then he would have kept going with the product rule. So product rule is the big picture, but within product rule, what else do we have? A chain rule. A chain rule. Which is why we do have to do my second d first plus first d second. But inside my d second, I have my outer keeping the inner unchanged times derivative of the inner. True? Okay. So the idea of the chain rule is it'd be a whole lot easier to look at functions in terms of compositions. Chain rule is to look at functions in terms of compositions, which is why last year, 2 years ago in pre-calc, in the composition section, which is actually section 1.8, because we're just now doing that both honors and regular have just made it through 1.8. Compositions of functions, there was not just composing, but also decomposing, not just finding compositions of functions, but taking complicated functions and breaking it down. All for the purpose of, or at least from my perspective, getting them ready for chain rule. So chain rule, lots of different forms, yeah? dy dx is equal to dy du times du dx. And this is actually the one where I saw my student, the one I was tutoring, able to ace it every time. Or the one that we mostly used last year. And I guess we could say the ones, but the AP mostly uses this one. That's why I'm a little nervous. And he wasn't taking the AP, he was just like in a general calculus class. Or maybe it was like a combined, I don't know. I don't remember exactly how the dynamics worked. But the AP loves this notation, and they make it in a way that you don't know the function, so you can't just know this way. You have to be able to deal with the function notation, which is why I make sure you see that. But then, of course, we have the U notation as well. The dilemma of the U notation, though, is can't the U have a V and the V have a W and the W have a, I don't want to use X or Y, a Z, right? An F of G of H of J of K of L of, I don't know. So I like the U notation because of its simplicity, but as soon as you have a U and another one, you're like, what do I do? So that's chain rule. We got it, right? Just kidding. Yeah, what's up?
Can you go back to the last slide?
Oh, the last slide?
Or the last, I have a question on it.
Yeah.
So for the second one where it says pdx of f of g of x, it's like missing a closed parentheses. Is that fine notation to do?
Oh, that's awkward. Huh. Is that something I typed? I mean, I have no idea where I might have stolen it if I didn't type it. Oh, I did type it. No, that was my bad. Thanks, Kevin.
Like, is it fine notation to not have the closed parentheses or no?
Which is why, well, I shouldn't say which is why. In your calculator, if you ever don't close all the parentheses, it just errors out and it doesn't like you. If you had it like in an AP question, I don't think I've ever seen that. Would it actually be incorrect? I would say it'd be more dangerous than anything. I don't think they would necessarily take off points just because of how minute it is and how it doesn't affect the meaning of the overall. But depending on what came next, it could affect the meaning. And so it's just dangerous to leave it off. But thanks for catching that. No, there's literally a typo on my part. All right, cool kids. So what's going on here if I want the direction is to find f prime of x? Because the nasty thing is this is an actual homework problem, and this is what you're given. Somewhat simulating the nasty stuff that an AP can give you in the weird way you can write it. So if they tell you f of u is equal to 1 minus 1 over u is equal to g of x, which is 1 over 1 minus x, and x is equal to negative 1. How do I find f prime of x? So you mean plug in everything. That would be great if I wanted f of g of x. If I wanted f of g of x. Specifically f of g of negative 1, right? But why do I not want that? Yeah. So I don't want to get a constant and then try to take a derivative, because derivative of a constant is just poof 0. Well, that doesn't help. So pause. You can do the plugging in thing, but can he go in yet? No. It's Make a note to yourself, this needs to wait till the end, right? Now, could you plug that into that? Uh-huh. But what if we didn't plug it in? What if we were just to tackle it right now?
So F prime of U.
F prime of U times U prime would technically be a form of the chain rule, and wouldn't I be trying to find dy dx, which would be f prime of x? Wouldn't I be taking dy du, the derivative of f with respect to u, and then multiplying by, wouldn't I be using that form? Do you guys see it? So then what would f prime of u be? You can do it. Okay, because that's just a 0, right? And then minus, and how are you thinking about rewriting this in your head? Okay, good. So bring down the -1, so +1, u to the -2, right? Is that okay? Times u prime would be, how would you rewrite it?
1 minus x to the negative.
So you bring down the -1. 1 minus x to the -2. Hold on. Well, why am I not done?
Chain.
What's within the u? Technically, v. So hold on, wait a minute. The notation starts to break down a little bit. So we can go ahead and, because I know you guys and I know your skills, we can go ahead and do a -1 right here and we'll be totally fine. Is this good as is? They're still u's. So wouldn't I have to go one step more and say, wait a minute, who is u? So that would be 1 over 1 minus x. Awkward. Can I just do 1 over 1 over as a reciprocal? Is that okay? So I have 1 over 1 minus x is just 1 minus x. And then a negative times a negative is a positive, and then 1 over 1 minus x squared. Oh, wait a minute. And yeah, can't I just reduce them? So I have a single on top and a squared on bottom, which would be the same thing as 1 over 1 minus x. And then what am I trying to find? All of this when x equals or at x equals 1 minus -1 is 2. It's a bit convoluted, but yeah, it's true. Now, if that made sense, let me show it to you in a different way. But first, John, go ahead. What's up?
So when it's 1 over u squared and I'm taking the 1 minus x, how come it's not squared anymore?
Oh, because I'm silly and I didn't put the square. Wow. Did I not even notice it? 1 over 1 over. Yeah, I just didn't put the square. Thanks, bud. So actually, what's that become? Awkward. So what happens when I plug in? Uh-oh, hold on. I heard 3 different answers and only one of them's right. What happens when I plug in? The derivative is constant, so it doesn't matter what x I'm at, right? Good, you're good? So let's see if you guys can use similar notation as this, but maybe a little bit more advanced. We're supposed to give you something like, I like this example? Yeah, nice. Okay. Some of you, yes, I know you could go for it right now. I'm curious. I'm curious if I was to teach this now. Obviously, I wouldn't have taught it this way to AB because they haven't seen any of this yet. You guys have. I'm curious how you would respond to the other way. And to be honest, the other way kind of depends on you being able to decompose this first. So I'm going to call this the decomposing chain rule. It's the chain rule, all of them are, but in a way that we're dealing with the decomposition of the functions. I'm curious if you can write this in terms of f of u and u of v and v of x. Make sure there wasn't a w, but there's not. I want you to decompose it. So So this function, I want you to think of it as an f of u of v of x. No derivatives. Not yet. Can you go back to pre-cal for just a second? And state for me, what would f of u of v, and b of x be in order to give me this composition of functions? This final result. Ready, set, collaborate in your groups. You have to look at it differently, and I'm curious if you can do it on your own, and then I'll show you what I mean. F of u, u of v, and v of x.
Yeah. I put X on all of them. B and X.
I thought it was cosine x equals I thought it was cosine x and then three.
Yeah, because cos of
Oh, whatever.
Hello?
I mean, if it was cubed, then that would be that one.
I know.
Cosine of first function.
Someone erased part of the video.
Can I come on up? Is that okay? My turn? Alright.
Was this on the AP exam?
It's changed, yeah. Some of the pieces.
No, like the I remember it. I mean, I remember how to do it.
How'd it go?
I don't think I used it.
Now technically, if I was teaching this to them, I would do F, I would do U, and I would do V. And you could keep on going as long as you wanted, because you could have a V and then a W, because the V could be in terms of W and the W could be in terms of X. You could have V and W and Z could be in terms of, sorry, W could be in terms of Z and Z could be in terms of X. And you could have as many composition as you want. You're just peeling off layers, right? So peeling off the cubed root, then peeling off the 17 minus cosine, and then peeling off, or ending with the 3x. So then how would the chain rule work? You guys see it? The chain rule, f prime of x would equal f prime times u prime times v prime. Does that make sense?
Yeah.
You would just have to do everybody. F prime times u prime times v prime. Now hold on, wait a minute. The notation just broke down. Where did the notation break down? Yeah, it kind of broke down there just a little bit in the sense of the f prime, f prime. So then depending on the teacher, they might actually reword this a little bit, and they might instead have just started right away with u, and then v, and then w. They could have done it that way, but that would have been kind of gross, because then u would have automatically had the v, so I don't like that as much. And guys, even in the chain rule itself, doesn't it technically have an f prime equaling and then an f prime? Right? But if you don't like that, you could have named him G if you want that a little bit better, if it's a little bit nicer. Or you could have rewritten this if you want it that way. As f of u of v of, like we could make it super, super proper. And then this is totally okay to have, because it's f derivative of the outside, keep the inside, derivative of the inside, derivative of the inside, derivative of the inside. But maybe if you guys don't mind, maybe I'll just do this and cheat. Aha! Okay. So I need my f prime, my u prime, and my v prime. So who's f prime? 1/3 u to the negative 2/3. What's u prime?
Sine of v.
Because derivative of 17 is 0, derivative of negative cosine is negative sine. Sine of v. And then derivative of 3x is? And there was no outer inner mumbo jumbo. That's why this notation, some people really like it. Now the hard part is it does take you a step away from f prime of g of x times g prime of x, and then once again the AP uses that notation. So I couldn't just do the chain rule this way. But it is kind of nice. Wait, it's not even right yet though. What would you have to do? Plug in. Plug in what? Who's v? Oh, 3x. Who's u?
17 minus cosine of dx.
Yeah, so technically what teachers usually do is they have them always go this direction. So they would say plug in the u first. So it would be 1/3, 17 minus cosine of v to the negative 2/3 sine of v times 3. Maybe somewhere in here they've had them start simplifying just to make life a little bit easier and not have everything all at once. But then they say at some point you have to plug in v is 3x. Now, could you have gotten that on your own? I hope so. Would you have seen this and would you have peeled off and done 1/3 to the negative 2/3 power and then times u prime, and u prime would have been a positive sine of 3x times 3? Yeah, theoretically. But this is a way of breaking it down and separating it. So all we have to do is, if they can do the decomposition of functions, just boom, 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 put it together and plug back in. Some ways it's nice, in some ways it's kind of messy, but that's the alternate way of doing the chain rule. And actually, my kid had no idea what f prime of g of x times g prime was, which would be awful for the APs. Remember, they give you the functions and you don't even know what they are, and it's all notation. You have to go look at a table or go look at a graph and pull out clues, and it gets kind of crazy. But I never saw him miss a chain rule derivative, which was kind of cool. I don't know. It's kind of weird, but kind of nice all at the same time. Anyway, well, let's say, ready, set, go find me derivative using whatever way you want. Don't make mistakes and make it match. With what? Okay, simplify it as best as you think. But I won't give you forever. P.S. I gave you ones where people make common mistakes. Just because you're BC. We are BC, so let's go hard, quick. The first one is actually a case where I see my kids, his teacher's way of solving chain rule as insufficient. Because up here, how to write this in terms of u, there's a u and a v separate, needs the product rule. He had a way of doing it. It just wasn't straightforward to me. So in this one, I'm like, the best way is just to know a simple, like, derivative of the outside, keep the inside, derivative of the inside. So much easier when you do second d first, just to be like, whatever, it's cosine of u times u prime. Like, it's so much quicker, so much more efficient. Or when you go to the second one, same thing, first d second. You would have your derivative of the outside, keep the inside, times the u prime. A concept that was totally foreign to him. The dilemma is, could there possibly be a way of simplifying this? Not easily, and you'd have to use like composite argument trigonometric properties, so I think you're good and safe to go there. They might have done something crazy, but it's not super straightforward. It's not even like a, some of you might be remembering cosine, right? Minus sine. It was a thing back in the day with trig properties, but these coefficients would need to be the same and they're not. So I can almost go back, but I can't quite, all because they had to multiply by two different ones. Any questions on number 1 though? Yeah, go ahead. Oh, 18 because I was doing product rule. And I was kind of keeping like 9 out. And so I was doing second d first, and when I went to do d first, derivative of sine is cosine of 2x times u prime is 2 times 9, 18. I went the other direction, first d second. That's where I got derivative of cosine is negative. That's how I got my minus. U prime was 5 times 9. But what do you notice me trying to show you one more time in number 2? Does the notation work in this one? Yeah. Because I have a square root of u. My u is 1 plus v squared. My v is a tangent. That's something that a lot of you guys tend to get mixed up. Because remember, don't get tricked by the trig notation. I have tangent of 2x squared. Squared is my next thing to tackle. And then my tangent. And then my 2x. A lot of you get this one switched and do the tangent before the square. Not a lot of you per se, but a lot of AB kids, I should say. But if you just split it up and decompose it right, it's like take derivatives. How do you take derivatives? Well, I need f prime, u prime, v prime, w prime, which is as easy as 1 over 2 root u times 2v times secant squared w times 2. It's as easy as that. Except what do you have to do? Plug and chug. So then you would start with your u. Well, actually, you could simplify, I guess, some of these, right? That'd be 4, and then 4 over 2, which is going to be 2. So 2 over root u will be root v squared times, yeah, there's a v up here and a secant squared of w. And then you would go plugging in your v's. So then you would have 2 tan of w secant squared of w all over the square root of 1 plus tan squared w. And then you would finish with your 2 tan of 2x secant squared of 2x all over the square root of 1 plus tan squared 2x. Wait a minute. 1 plus tangent squared, is that a thing?
Yes.
Mm-hmm. What is it? Are you sure?
No.
How do you know for sure? What's the one that you're for sure of? How do you get to the tangent squared, secant squared one? Tangent squared is sine squared over cosine squared, right? Do it to everybody. So wouldn't that be tangent squared plus 1 is secant squared? So I can change him to be secant squared? So then I can square root secant squared to reduce? Now careful. What do you have to be aware of? What's the square root of a square? So when I have 2 tangent of 2x secant squared of 2x all over absolute value of secant of 2x. Sorry, I cannot do the 2x today. How do I reduce secant squared of 2x all over absolute value of secant? Wouldn't this be a positive? And when I reduce, can't secant be negative? So how do I resolve that? Wouldn't I need him to be an absolute value up there? Does that kind of make sense? So I could make him secant squared, which I could reduce the square root, but I have to do it with an absolute value. And then when I go to simplify, I can simplify, but I need him to stay positive. So if I cancel out, I get rid of the absolute value and the squared. the negatives can come bombarding in, except they're not allowed to. So once again, do you have to do the chain rule with the U's and the V's and the W's? No, but it is interesting, especially if you find yourself continually making mistakes on chain rule. With chain rule, though, we get to kind of go back to parametric for a second. What? With chain rule, we get to go back to parametric. Parametric equations, x equals y equals two-dimensional motion. Remember, x equals y equals for each function. You have horizontal change and you have vertical change all happening at the same time, something that's going out and up, or down and over. Here's the cool thing. If I'm looking at a set of parametric equations, an x and a y, and I want to get a dy dx, it's going to be awkward. It's going to be awkward because x is in terms of t and y is in terms of t. They're in two separate places. How on earth do I get one combined derivative, one combined slope of the tangent line? Which is on a graph for a parametric curve that's moving out and over all at the same time. Time is some like non-existent, not on the graph variable. I shouldn't say non-existent, but not visible. Third variable called the parameter. Does it make sense that dy dx would equal dy dt over dx dt? Well, check it. If I were to multiply the dx dt to the other side, does it make sense that dy dt equals dy dx times dx dt? Yeah, it's chain rule. That's the crazy thing. It's a weird application of the chain rule. I can take my dy dt, I can decompose it into a dy in terms of x and then a dx in terms of t, and then I can just rearrange it to get what I want. And I'm like, hey, that's just y prime. Hey, all I have to do is y prime of t all over x prime of t. To find the slope of the tangent to a two-dimensional curve, I can just take y prime over x prime. Which is kind of crazy. And it's kind of crazy that it actually comes from chain rule. But the nice thing is you don't really need to know where it comes from. It's just kind of cool to see where it comes from. You just need to know how to take a derivative of a parametric curve, y prime over x prime, and it all works out. Or I should say the slope of a path given parametric equations. Now the crazier part comes, how do we take the second derivative? The crazier part kind of comes, how do we take the second derivative? Now we know with implicit differentiation, isn't the second derivative even harder than the first? We haven't reviewed implicit differentiation. Maybe I'm jumping in the deep end a little too much. But you have like y squared plus x squared is equal to 2xy, and you have to take a derivative as it is, right? And you get all these dy dx's, get the dy dx by itself, and you're like, whew, and then you move everything else over. But then if you have to take a second derivative, don't you get some more dy dx's that you have to go back and then plug in and then blah, blah, blah. So we're kind of used to second derivatives being messier of more complicated functions. And it kind of makes sense there has to be another derivative. You guys see the ddt on top, right? But do you know why that's a problem? Why we have to divide by another dx dt? What would notation give me? If I was to take that derivative, wouldn't that be a d squared y over dx times dt? Is that right for a second derivative? So how do I get rid of what I don't want and get what I do want? If I multiply by a dt over dx, does everything work out? So the weird thing with parametric equations is this third variable, once again, this parameter, that kind of makes things work a little bit different than we're used to. We take a first derivative by taking the derivative piece by piece and dividing. That seems super straightforward. Yeah, fine, let's memorize it. Ooh, it actually has a meaning. It comes from chain rule. This one gets even crazier. Do you guys know what most people tend to forget? Always, always, always on the second derivative? Him. Because he's so random, he's so extra, he's so out there. The nice thing is in your book, I'm not even sure if they really show you parametric equations. This isn't a Endeavor card. I just kind of like when we're learning chain rule being like, hey, it's going to help us when we start doing two-dimensional motion and give us a way to take derivatives of parametric curves and not just of the normal ones we're used to. But guys, that's enough for today. Maybe we'll play around with parametric equations a little bit tomorrow. But the goal of tonight is, don't worry, this would be the very first time it would have been introduced in our calculus book. Play with chain rule. Maybe use the U, the V, the W. Maybe just keep thinking the outer and the inner and the inner of the inner and the Matryoshka doll idea. So what's the idea of the chain rule? To find the derivative of a composition of functions. Take the derivative of the outside, and then you peel it off, keeping the inside the same. Then times the derivative of the inside, keeping his inside the same. Then times the derivative of the inside, keeping his inside the same until the only inside is x, and that's the derivative of this. Bye, guys. Chain rule up tonight. Let's see how it goes. Bye.
You're like that one person who brings change and says, it's exact. Yeah, it is. I used to wish it. Oh, are you leaving your stuff here? Yeah. Okay.
Pause.
Can I show you?